Hello everyone, my name is Alvaro, and in this video we will be solving another problem from the blind Leetcode 75 list. Today we will be going over problem 98, which is called Validate Binary Search Tree. And this is one of my favorite problems from binary search trees, since I think that it deals with recursion kind of nicely, and you just have to look at the actual properties of a binary search tree, and this does not require any complicated algorithms. So let's take a look at the problem statement and then a little bit of the code that's given to us. So the problem statement says, given the root of a binary tree, determine if it is a valid binary search tree. A valid binary search tree is defined as follows. The left subtree of a node contains only nodes with keys less than the node's key. The right subtree of a node contains only nodes with keys greater than the node's key. And both the left and the right subtrees must also be binary search trees. Okay, so this example is true because 1 is less than 2 and 3 is less than 2. This example should be false because while this is true, 4 is less than 5, but any number that's located in the right subtree of this tree should be greater than 5. So in this case, for example, this subtree right here is a valid subtree, but this node right here is not. Okay. So input root, great. Explanation, yep, that's totally fine. Okay. So if you want to try this problem by yourself, now will be the time to pause the video. And now I'm going to discuss the way to solve this problem. So, what is the big idea here? So, one of the approach that I was thinking about is thinking about different values. So, for example, if we are in the root, right? The root can have any value whatsoever. For example, if we start with a 2, well, so we can say that there are two bounds. There's a lower bound and an upper bound. The root has a negative infinity lower bound and a positive infinity upper bound. Let's see if there are any actual, the number of nodes in the tree is in the range between 1 and 10 to the 4th. Okay, so we can make the lower bound 0 and the upper bound 10 to the 4th plus 1. So anyway, so the lower bound here, theoretically, I guess we can say it's negative infinity and positive infinity, right? And once we get to the 2, the left subtree, whenever we go to the left subtree, the upper bound will change, right? The upper bound will now be this number right here, minus 1. Or, it depends. So what I'm going to do is, for example, suppose that we start with a 2. What I'm going to say is that the upper bound will be this number, and all numbers must be less than this. What you can also do is simply just make the value here minus 1, because I believe we're dealing with integers here. Well, it doesn't say that. Okay, so okay. So basically, the bounds here on this root is negative infinity and positive infinity. Whenever we go to a left subtree of a node, then the left subtree's boundaries will be the same negative infinity on the lower bound, and the upper bound now will be the value of the parent. So any number right here must be less than negative infinity and greater than negative infinity and less than 2. On the other hand, the opposite thing happens when you go to the right subtree. The upper bound stays the same as the parent, but the lower bound now becomes the parent. And we will go like that and like that. And whenever we reach a null node, so whenever root is equal to 0, as we travel recursively through the tree, then that will return true. That'll be our base case. So if we run the example, for example, on example 2, here the bounds will be negative infinity and positive infinity. We go to the left here, and we have to check first, obviously, that this number right here is within bounds, and if it's not within bounds, we return false. Else we check the left subtree and the right subtree. And if both of these are valid subtrees, which null nodes are valid subtrees, since they're the most basic example, then this is within bounds. And then we go to 4. So here, like we said in the root, the negative infinity is the lower bound and the positive infinity is the upper bound. And then we go to 4. Now, as we said before, the lower bound now becomes the parent node. So the lower bound will be a 5, and the upper bound is positive infinity. And since this number right here is not within those bounds, we simply return false. If it was within the bounds, then we would have to check each element in, we would have to check if this is the valid subtree and if this is a valid subtree as well. But we stopped there since we found an element that's not. So let's see. So we're going to define another method that will take a root, and then it will also take a lower bound and an upper bound. So let's define check BST. So this takes a root, a lower bound, and an upper bound. So if root is equal to none, then we return true. So that'll be our base case. Now, if root that value, right, is greater than the lower bound, and root that val is less than the upper bound, then that's when we check left subtree be equal to check BST root dot left. So here we check the root dot left, and like we said before, the lower bound is the same, but the upper bound now becomes root dot val. So lower bound stays the same, and that, and right subtree, we just check it as well with root dot right. And remember, now the thing that changes is the lower bound. And then we return whether left subtree is equal to true and right subtree is equal to true. I realize that I can say left subtree equals right subtree equals true, but I think this is easier to read. And in the other case, we simply return false. And that should be it. So now if we just call this method, so we can say return check BST root float. I think this is in Python negative infinity. I think that's how you define infinity here. And float infinity. And then this should work. There you go. Obviously the runtime is a little bit inconsistent here, but as we go, there you go. See, faster at 97.12%, and that will be how we do this problem. Like I said before, the lower bounds, since we have the bounds here, they can be 0 and 10 to the 4th plus 1. I prefer to use negative infinity and infinity just because, you know, it makes a little bit more sense conceptually, but any number that's lower than 1 as a lower bound, and any number that's higher than this as an upper bound works completely fine. So anyways, let's get to the space-time complexity and the runtime complexity of this algorithm. So the runtime of this algorithm is big O of n, because in the worst case scenario, we visit every single node of the tree. And the space-time complexity will be, in the worst case scenario, will be a tree that is completely skewed, which we have seen in previous previous problems when I mentioned the worst case scenario. So a skewed tree will be a tree that each node only has one child. So if it has n nodes, then it goes n levels deep. So for example, 2, then a 3, and then the 1, instead of being a child of the 2, will be a child of the 3. In the worst case scenario, we go n levels deep in the recursion, and since we count recursion calls in the stack trace, in the stack, recursion stack, or whatever it's called, since we count those for space complexity, then the space complexity of this solution will be big O of n. And that's about it. I hope you enjoyed the video and that you found it helpful. Definitely one of my favorite problems, and it's something that you might get asked. It's a question that you might get asked on internship interviews for good companies, so definitely want to keep an eye out on. So yeah, I hope you enjoyed the video, like I said before, and see you in the next one. Thanks for watching. Bye-bye.